Let's talk a little bit about electric field basics. So you're seeing an electric field here that I've drawn on the two-dimensional screen. I've randomly chosen to draw a bunch of electric field vectors of different sizes in different directions, and this field is being set up by something, some set of charges that I'm not even showing you. I don't really care. But I do know that at each one of these, at each point in space here, I can define a number and a direction that would indicate the value of the electric field. So for example, here at point P, if I were to investigate that point in physical space, I could label that point right there with a vector, and it's pointing down and to the left. And I'm saying that the magnitude of the electric field at point P is 10,000 newtons for every 1 kilogram, and the direction of the electric field is down and to the left. Of course, we would want to put an angle on there if we wanted to get specific, but I'll just say down and to the left for now. And the whole idea with the electric field is that it will allow us to know the electric force that is applied on a charge if we were to come and put a charge at that point P. So if I were to just pluck a charge from somewhere, maybe a positive charge here with this little red dot, and decide to place it right there at point P, we would then be able to calculate exactly how much force and in what direction that charge experiences from the presence of that electric field. And again, keep in mind, I have not specified at all. We have no knowledge about what's creating any of these field vectors in this particular problem, and we don't need to know once we know the value of the electric field. That will allow us to find the value of the electric force. Now, the other thing that's important to state is it's going to matter if you put a positive charge at point P or a negative charge at point P. If you put a positive charge at point P, so again, imagine this little red dot is a positive charge, and I place that right at point P, then the direction that that positive charge will feel a force will be pointing directly in the direction that the arrow is pointing. That's the convention with the electric field. The field vectors point in the direction of the force that a positive 1 Coulomb charge would feel if placed at that point in the field. And likewise, if you put a negative charge there at point P, you would feel a force 180 degrees the other direction. So if I can't change the color of this, actually I think I can. No, I can't. So if this little red dot now was a negative charge, and I placed that here at point P, it would experience a force up and to the right instead. But the magnitude would still be the same, assuming they were the same magnitude of charge. So let me just kind of write this. For example, if charge 1 was something like plus 3 coulombs, and then charge 2 was something like minus 3 coulombs, think to yourself real quick, maybe pause the video, how many newtons would be applied to charge 1 and how many newtons would be applied to charge 2? Try that. Go ahead. All right, so pretty easy problem. I'll show you something to watch out for, but you just multiply. So the charge value, charge 1, some little test charge we're going to place at point P is 3 coulombs, and the electric field strength is 10,000 newtons per coulomb. You multiply it together, the coulombs cancel out, and we're left with 30,000 newtons. Now be real careful. Watch what happens. I'm going to do something that is like technically incorrect. Maybe you can see what's happening here. Okay, what if I did this? Coulombs cancel, and you reported your answer like this. This is misleading. Pause the video and see if you can see what's a little bit misleading now. Well, hopefully you're seeing that this negative sign, that really doesn't have a meaning. That's not the direction of the force. This is not a one-dimensional problem where you think that, hey, this would be either down or maybe to the left or something like that. Along a one-dimensional line. So negative 30 newtons would imply a force to the left completely, or negative 30 newtons might imply a force straight downwards completely, like you might have seen before with one-dimensional problems. So to be more technical, the way you'd do this is you'd say, hey, the magnitude of the electric force is equal to the magnitude of the charge times the magnitude of the electric field. It gets annoying to write all those absolute value bars like that to indicate the magnitude, but to be super correct, that's basically what you would do. Okay, to get the direction, of course, you just, well, look, it's parallel to the force vector. It's either going to point along with it, if it was a positive charge like this, down into the left, or it's going to point back the other way with 30,000 newtons and up and to the right. And that's all there is to it. Okay. So don't overcomplicate it. Once you know the value of the field, you can plug that in, multiply by some charge that you place at that point, and you can always find the electric force on a particular charge anywhere. So just to formalize that, the electric field represents the magnitude and direction of the electric force that a positive 1 Coulomb charge would experience if placed at a specific point. And the formula is here, and again, most of the time we just write it like this, just for clarity, but it is representing magnitudes. And a similar idea is gravitation. So if you look here, maybe you're on the surface of the Earth, and you know that the gravitational field strength is 10 newtons per kilogram pretty much everywhere. And so how much force will a mass feel if placed at some specific point? That's going to depend upon the mass that you place at that particular point. Just as the electric force on a charge depends upon, well, the amount of charge you place at some point. Remember, this is the charge we're placing in some external field. And this is a mass we're placing in some external gravitational field. What's setting up this external gravitational field? Well, the Earth. And what's setting up this external electric field? Well, I haven't told you yet, but it's going to end up being other charges that exist. Okay. So, for example, we could come along and place, I don't know, maybe a 4 kilogram object right up here. Something kind of like, I don't know, some box or something that's 4 kilograms. And you know easily from studying physics that the force would be mg, and you'd get 4 kilograms times 4 newtons per kilogram. And kilograms cancel, not times 4 newtons per kilogram, times 10 newtons per kilogram. And you would cancel out the kilograms, and you'd get 40 newtons. And you can see here, it's very standard in physics just to do force gravity is equal to mg in the same way we kind of just write this formula like that. And we always know that the forces point straight down when we're doing gravitation, but in the electric field it's a little bit more subtle because you have to look at the electric field vectors and reason which way the electric force would be pointing, kind of based on the context of the particular problem. And I'll illuminate that here in just a second with some other examples. Okay, so there's the basics of kind of what the electric field is about. And now let's take a look at two classic scenarios that you need to know. One of them is about a constant electric field and how we easily set those up. And the other is about electric fields that are set up by what are called point charges. So let's take a look. So let's start over here on the right. And you can see that we have a charge, capital Q, that's setting up some electric field. This is a point charge. It's at some place in space. And we use the variable capital Q to denote charges that are going to be setting up fields, and then typically lowercase q for charges that are going to be responding to those fields. So for example, we could now take another charge, maybe place it way over here at that point. I'll call that little q, and now that charge would experience an electric force that's occurring because of the presence of this other charge, capital Q, over on the right-hand side. And if we wanted to, we could calculate that, and it would be lowercase q times the electric field value, field strength that is created from capital Q at that point. Now, interestingly, this lowercase q, it also sets up its own field as well. So we could draw field vectors for that guy as well. And this positive charge over here would experience an electric force from the presence of this other charge here. But typically, we don't do that. It's in the same way that we don't really care about the forces that are exerted back on like the planet Earth from a mass that we place in the gravitational field that's set up by the Earth. Because we're not analyzing the Earth, we're analyzing the mass that's moving around Earth. In the same way here, we don't really care about what's happening here, and oftentimes we're just considering that this charge that's setting up the field, capital Q, is just like pinned into space. It doesn't move, it can't move. And then this little charge here is the thing that's going to be responding to that field. Okay, so just watch out for that. But now we could go and take this little charge Q and move it anywhere we wanted it in this field. And we notice that both the magnitude and direction of the force it would experience would be changing depending on where we placed it. And these field vectors are pointing out radially outwards. Now, if you're taking AP physics, typically the College Board requires people to draw the field vectors, I should say, electric field vectors. So at each point, you come along and you draw a field vector that represents the magnitude and direction of the electric force that a +1 Coulomb charge would feel if placed at that point, and I've done that here. But it's also important to know how to draw field lines, even though they don't have it specifically in their curriculum. And the way you do that is you just connect these field vectors like this, and you put like lines like this. I tend to like to draw both, but I think it's important to learn how to draw field lines and also how to draw field vectors. And you can tell the strength of the field by taking a box of like some area here. We'll just take like, I don't know, a little box like that, and just find the density of field lines that are kind of penetrating that box, and then draw the same box somewhere else, same size box, and you can see that there's less field lines kind of going through that. I should probably draw more lines like this. And there's some math that we won't learn that would kind of allow you to see that. But you can see here in this upper box, there's more field lines kind of intersecting this little box here. And down here, there's less. And so where the density of the lines is higher, there's a stronger field strength at that location. You're really close to the charge. And then the further away, it's less. Okay, now you saw in my picture from before how the electric field strength was decreasing as we got further and further away from the charge. And that's exactly what happens. But we want to be more precise mathematically. So what kind of relationship do we find between the electric field strength and distance from the center of the charge? So I've kind of drawn that here. Here's like the exact center of this charge. And we see point 1 here is at a distance d away from the center of that charge. And then point 2 is 3 times as far away. Okay? And I'll focus your attention on two possibilities. Either the electric field is going to be inversely proportional, or the electric field will be inversely proportional to the square. So an inverse square law. Which one is it? Think about it, and there are some helpful simulations. One of them on PhET, if you've gone there, the University of Colorado Boulder, and you can go check out the sim called, I think, Charges and Fields. So just type in Google, Charges and Fields, PHET, and you'll see a simulation there, and you can play around with some electric field sensors and kind of run this experiment yourself and see which one it is. So take some time to do that if you haven't done that, and then come back, and then we'll see the answer. All right, well, I decided to bring up the PhET sim here for you to take a look. And here we have a positive charge setting up a field, and now I got this little sensor. And as I move this sensor around, you can see the electric field is changing its magnitude and direction. And if I get really close, the field's strong. And as I come further out, the field is much weaker. And the units of the field here are in volts per meter, as you can see. And we'll learn about that at a later date. We'll use newtons per coulomb for now. But let's take a look. If I am at some distance d away, maybe like right there, I got about 4 newtons per coulomb, or 4 volts per meter, for the electric field strength. And let's see what happens when I double the distance. So I have a helpful little ruler down here. So I'll just double the distance all the way out to the end of that ruler. So here we're at about 4 of the value for the electric field. Now double the distance, and we're at 1 for the electric field value. So we went from a strength of the electric field from 4, and then we doubled the distance, and now we have an electric field strength of 1. What's happened? Well, the electric field has changed by a factor of 1/4 as much as it was before. We doubled the distance, and now we're getting 1/4 of the amount of field strength. What kind of relationship is that? Is that an inverse or an inverse square? Pause the video and select which one you think now. Perfect. It's the inverse square. You got it. Now, answer this specific question. Point 2 is 3 times as far away from the center of the charge as point P1. So how would the electric field strength compare at P2 compared to P1? What number would go right here? Pause the video and get some practice on proportional reasoning. All right, well, hopefully you got it. 1/9. So the distance went from D to 3D. Therefore, the electric field strength would go from E to 1/9 times its original value there. All right, so you can see now, when you have a point charge in space, it matters how far away you are from that point charge to see what the value of the electric field will be. And the direction, of course, is radially outwards. Now, if you had a negative charge, let's just replace this from a positive and turn this into a negative charge, and I'll erase this arrow here. What happens then? Okay. Well, if you think back on the definition of what the electric field was, it's the magnitude and direction of the electric force on a +1 Coulomb charge. So if we placed a positive charge right here at, say, P1, which direction would this little guy feel a force? Well, it would be attracted to the capital Q, which is now a negative charge, and it would feel a force going back like this. I need to draw it radially correctly. It would feel a force going back like that. It would be larger based on my previous drawing, but the main point I'm trying to share with you is just that the force is backwards now. So electric field lines end up going into negative point charges like this. So if I were to draw all these field vectors, it would start to look something like this. Of course, they would decrease out here and get smaller. And then you could draw the field lines like we did before, and you'd connect all these things together and you draw your arrows like this. Okay, so electric field vectors then, or sorry, electric field lines go into negative charges and they come out of positive charges because of that sign convention that we have chosen at the very start. Cool. Okay, so far we have realized a dependence between the electric field strength E and then the distance R. It's inverse square, and there's one other thing that matters, and of course there's a constant as well. The constant is Coulomb's constant, and we'll put that right here, okay? Again, it's around 9 times 10 to the 9th, and then you get the units right. And then the other thing that matters for the electric field strength, think about it for a second. What could it be? And it's pretty intuitive to get it. It's the amount of charge that you place at some point in space. So capital Q, how much charge do we place somewhere? So we'll put that here. And it's a direct proportion. You could go back in the PhET sim and do that simulation, and you'd see if you double the amount of charge or triple the amount of charge that's setting up the field, you'd get double and then triple the field strength. Cool. All right, so there we have it. Now, the key idea, though, is that this is the magnitude of the electric field set up by a point charge. So we'll write that. And to get the direction, it's just radially out in all directions from a point charge. And we'll see certain geometric configurations of charge where that will be helpful, but we don't want to do that in this video here. All right, so that's the basics of the field set up from a point charge. Now the other way you need to be thinking is parallel plates. So these are like two metal plates. Kind of draw a three-dimensional picture just to help you really see what's going on. Something kind of like this, where we put positive charge all along the top of the plate, and then we put positive charge on the top plate, and then a bunch of negative charge on the bottom plate. Assume equal positive and negative charge there. And the question is, well, what happens in between? And you can work this out. We won't do that, but you can prove with a bunch of math that you end up getting a constant electric field in between these parallel plates like this. So we'll draw that. It's typically done in the following way. Remember, field lines come out of positive and go into negative charges. And those are the field lines. The field is constant. It's very important that you realize that. You don't need to prove it, but you can if you want to do some fun math. And then on the edges, there's actually what's called an edge effect, and these lines kind of bend around like that. We won't worry about really solving problems with math in that sense, but you should be aware of this edge effect, that the field lines do kind of bend around like that. But inside of the plates, and as long as you're in between, kind of towards the middle somewhere in there, and you've got significantly kind of like long enough plates, some length L there, then the field's going to be constant. Okay? Doesn't matter where you go. You could go, let me just put some dots here. You could go here, here, there, really close there, anywhere. Any of those points would have the exact same value and direction for the electric field strength, okay? And it would be pointing down everywhere. It's like gravity, 10 newtons per kilogram, and this might be 100 newtons per coulomb everywhere in those parallel plates. Now, you might be thinking, all right, well, is there a formula for that? Does that formula include all of these charges somehow? No. Well, I mean, it can, and if you go through all the crazy math to do it with first principles. But in no way are we going to do that. That's way too cumbersome. For our purposes, we're going to do something very simple. And parallel plates will be set up in a cool way. And the way we do it is we take some conducting wire on both sides here, and we hook that up to a battery. And here's the symbol for a battery that we use in physics. Positive side of the battery and negative side. And batteries have voltage. So maybe we have something like, I don't know, 20 volts. And we haven't talked about voltage specifically, but hopefully you have an intuition from just using batteries or something that has something to do with like electric phenomenon. Imagine we had a 20 volt battery, okay? And then we just hooked that up to these plates. You could literally do this at your house with a battery and like tin foil. Don't do that, but it would heat up and it might burn you. So don't do that. But the voltage might be 20 volts. And then the distance between the plates, we could also talk about that. Let me get rid of some of this stuff here, just so we can label on our diagram some distance d, like this. And maybe that's like a pretty small distance, something like a centimeter, I don't know. So 0.01 meters. And what's really cool is to get the value of the constant electric field in between parallel plates, when you hook it up in this way, there's this cool formula that we'll talk a lot more about at a later time. I'm just kind of giving it to you today to build up this kind of quickness in the thinking here. And it's V equals ED, VED. See, it's easy to remember, and we can now find the electric field strength. Again, to make everything technical, you'd put absolute value bars around everything, but I don't want to get really involved in that here today. We'll just realize that to find the electric field magnitude and strength here, you just divide. So it would be 20 volts divided by 0.01 meters. And then you do that, and you'd get 2,000. So this would now be an electric field strength of 2,000 newtons per coulomb. The magnitude of it, right? Now, what's the direction of that field strength? Well, look at the picture. Remember, field lines go out of positive and into negative charges like that. So if we wanted to write this as a vector in its full glory here, we would say that the electric field as a vector in these parallel plates, or in between these parallel plates, is equal to 2,000 newtons per coulomb in the negative y direction. And now we could solve problems with it. And if you were going to plug those into numbers, of course, you'd set up a coordinate system. So up would be positive probably in terms of space, and then down would be negative. Or you could reverse that, it doesn't really matter. And then you could go ahead and solve for some problems. So let me kind of give you a sense of that here now to kind of finish out this video. All right, so let's just finish up here by asking you just a few simple questions about this parallel plate configuration with a constant electric field. There's some classic problems that we like to solve. So we've got a battery here hooked up, 300 volts, and we've got a charged particle, a positive particle. It's going to come in to the field right here, moving at some constant speed. Let's ignore gravity. There's no gravity here. So this particle comes in, it's about to enter the field right in the middle, and we want to know what's going to happen to it. So step one, solve for the electric field in between the plates. Go ahead, try that. Okay, hopefully you got it, and you just divide the voltage of the battery that's setting up this field here by the distance, and you get 10,000 newtons per coulomb. Notice how you also get volts per meter. That's another more common unit for the electric field, but we'll just stay in newtons per coulomb here today. Now the next question is really important. I want you to imagine the path of this charged particle, this positive particle, and trace it out, draw it. What do you think it's going to do? I'll give you a couple options. Do you think this charged particle is going to come in the field and just go straight through unaffected? It's one possibility. Maybe it'll come through and kind of go down and slope down like in a parabolic path. Maybe it'll come like this and do the same thing and slope up in a parabolic path. Maybe it'll go straight down like in a diagonal line, or maybe straight up in a diagonal line, something like that. That looks kind of messy, but hopefully you understood those choices. Either it's going straight through, parabolic down, parabolic up, or straight line diagonal down and straight line diagonal up. Go ahead and make your choice, and then we'll take a look. Okay, well, the answer is parabolic down. However, I hope you didn't just kind of like guess at that and had a general feeling. you should know why from physics principles. So maybe pause again, and now that you know the answer, see if you can kind of reason through why that must be the case with physics principles, and then we'll look at those principles together. All right, so here are the two main concepts. We need Newton's second law, and then we need the equations of motion for, this is important, constant accelerated motion. And that's the key thing you needed to see here, was that this electric field is constant everywhere. What does that mean? Well, it means that the electric force on this charged particle will be the same strength no matter where it is along the path. So it gets shot in horizontally like this, and then immediately once it enters the field, it's feeling this downward pull, a constant downward pull as it tries to go horizontal. And we've seen before in previous physics with kinematics that when we have some initial horizontal velocity, but a constant downward pull, say from gravity, we get this downward parabolic path. That's exactly what's going to happen here. Now, how you would end up calculating that? Well, you'd have to find the net force, which would be QE on the charged particle. So you take the field strength E, which again you could find from the battery's voltage and this distance between the plates, which is pretty cool. And then you divide by the mass of the particle. That would give you the constant acceleration that you could then plug in over in this formula and then solve for stuff. Of course, you'd realize that as well. There's no initial vertical velocity. And then you would need to be given something about how fast this particle was shot in to determine everything about the answer. If it was shot too slow, it would end up, striking the bottom plate here. And if it was shot just at the right speed, it would end up striking or just about leaving right here. And if it was shot too fast, it would still curve down in a parabola, but it would eventually make it out of the field. And that would be dependent upon how fast you shot it in. So we'll look at that type of problem a little bit later when we have more time, where you can fully work out like all the cool things you can solve about this problem, which is a classic problem. All right, so there you go. That'll wrap it up for this video. Take care, and we'll see you next time.